All right, welcome back to Math 160. Happy early Thanksgiving. But of course, we must continue on, and we are going to look at Chapter 8, Estimates and Sample Sizes. So be prepared. We're going to kind of go around and, share the time in reading through these notes. Like I mentioned previously, luckily there's not a lot of notes we have to handwrite. It's just kind of going through it and making sure we understand exactly what it is that we're reading. All right, I'm going to switch over to my notes. And yeah, welcome. Good morning. It's great to see all of you, especially so close to vacation. It's really, really, really nice. Let's get started. 8.1, estimating a population proportion, inferential statistics. Let's start with Sam. Would you be so kind as to read through the information pertaining to definitions of inferential statistics? So I'd love it if you just took this first 4 notes.
Gotcha. Okay. Number 1 involves the use of sample data to form generalizations or inferences about a population. 2, sample data is used to estimate the values of population parameters such as population proportion or population mean. 3, hypothesis testing, test hypotheses or claims made about population parameters. And 4, in inferential statistics, we are trying to estimate a population parameter with an unbiased statistic from the sample.
Thank you so much. Perfect. So that's essentially the foundation for what we're attempting to do. We always know that when we collect sample data, we're doing that. We're using that information to help us make inferences or generalizations about the bigger population, right? That's why we use samples. Think about the fact that we've discussed in the past how hard it is to collect data from the vast population. So we narrow it down. We say, let's collect data from a sample so that it's a replica of the population. It's easier to manage, it's cheaper, it's less time. And then hopefully we can make some unbiased generalizations about the population. So that's essentially what we're doing here as researchers, as statisticians. Okay, let's continue on. We have estimating a population proportion. Kelly, would you do us the honors of reading the definitions for estimating a population proportion?
I was just starting to read as I'm mute, sorry.
It's okay.
Point estimate, a single value or point used to approximate a population parameter. We will use p hat is the sample proportion for p, and x bar is the sample mean for u. Confidence interval or interval estimate, a range or interval of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated as CI. Confidence level, the probability is 1 minus A, where A is the amount of error that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. The confidence level is also called the degree of confidence or the confidence coefficient.
Thank you so much. There's a lot going on here. First, point estimate, single point estimate. P hat, sample proportion for P, X bar, sample mean for mu. That one we already knew. We knew this a long time ago. The new piece of information is this P hat. We haven't seen that yet. So P hat represents the sample proportion for the population proportion P. So we are going to look at confidence intervals, right? It's a range of values. I have a little diagram below where we have our point estimate, and we're hoping that it's somewhere in between this interval, right? We're going to say, we're going to essentially estimate where this point value lies within this interval. Your confidence interval, the probability is 1 minus alpha. Now, alpha is the amount of error. So that's going to change. Sometimes you will allow for a 5% error. So you're 95% confident. Sometimes you'll allow for 10% error, so you're 90% confident. Sometimes you'll allow for 2.5% error, right? So you're 97.5% confident. So you see what I'm saying here? Can you see the balance between error and confidence? We're going to see that on the next page as well. And then of course, the confidence level is the degree of confidence or the confidence coefficient. Let's turn the page and you'll see what we are referring to. I'm going to close this highlighter. I think we're good for right now. Oh, almost.
I have a quick question.
Yes.
What's the, I know this is kind of dumb probably, but what's the difference between a population proportion and a population parameter?
The population, so a population parameter specifically means a value that describes the population. So when you hear the phrase population parameter, you can think population proportion, the population mean, the population standard deviation. Those all take on numerical values that describe the population. That's the difference.
Okay.
All right, cool. And then this chapter, we get to play around with proportions. So we're going to see a lot of that. We're going to see the means, proportions, that kind of thing. So we'll play with those population parameters, but in the sense of collecting sample statistics, okay, and point estimates to estimate the population. You'll see. Cool. Turning the page, let's move on to Emma. Would you read B, this section here, on interpreting a confidence interval estimate?
Take a look at the following statement and interpret its meaning. The 0.95 or 95% confidence interval estimate of the population proportion P is between 0.828 is less than P is less than 0.872. Interpretation. This means we are 95% confident that the interval from 0.828 to 0.872 usually does contain the true value of the population proportion P. This also means if we took many different samples of the same size and constructed its corresponding confidence interval, 95% of them would actually contain the value of the population proportion P.
Yes, excellent. I hope that you're making the connection between that statement and its interpretation. All right. This confidence level, it's essentially saying how confident we are that the population proportion falls within this range. And then, of course, if we collect different samples of the same size, we are confident that 95% of them would actually contain the value of the population proportion P. There's a lot to unpack here. I put stars next to this because I really want you to come back to it. As you interpret your confidence intervals, this is a good page to come back to, just to look at how we wrote out our interpretation of that statement, the confidence interval statement, so that we can be consistent every time. Beautiful. Part C, we have critical values. Anthony, would you read all of this section, part C, on critical values?
Critical values are essentially cutoff values that define regions where the test statistic is unlikely to lie. You'll find the associated z-scores for these critical values. 2, a z-score associated with a sample proportion has a probability of alpha divided by 2 because the area alpha is divided between the two tails. Below is a visual to help demonstrate this idea.
Yes, thank you so much, Anthony. And the really cool thing about this is we've seen this already. So when we were looking at the sampling distribution of sample means, we talked about, a couple examples that had like the middle 95%, right? So we would say, okay, we are looking at the middle 95% and what are the z-scores pertaining to that bounded region? We would say, okay, well, that means I have 5% left to split between the tails. So immediately when we drew our curve, we would label each side as having 2.5% of the population within these regions, the lower bound and the upper bound, right? Okay, so we'd go to our z-score table and we'd find the associated z-score for that region. Same exact idea. If you are 95% confident, you're within the middle 95%, which is why we do those problems to prepare you for this section. But the great thing is now I've given you a critical value table. So instead of having to look up those very common middle percentages, we actually have a table that you can use to help you identify those particular z-scores, okay? But keep in mind, that's where it comes from. So you're looking at the middle percentage and the rest is shared between the two tails, which is why you're going to cut them in half, of course. Turn the page. And notice at the very top right-hand side, you have your common critical values. Please keep this in mind. This is going to be a very helpful table as you move through. Okay, definitely keep these in mind. These are the common confidence levels that you'll see. 90%, 95, 98%, 99%. And then these are their associated critical values. All right. If we were to look at the z-score table, we would see that these are the associated critical values. Except for this first one, we probably see 1.65, and this last one, we probably see 2.58. But for this section and moving forward, let's use these critical values when we talk about confidence levels. Okay. Perfect. So we're just going to practice looking at each condition. We already have the curve, check, shade the region, and then find the critical values. When we are referencing the 90% confidence level, we're looking at the middle 90%. And originally we weren't sure how far left or how far right that went. But according to our table, our confidence level of 90% has a critical value of 1.645. So we're going to plot 1.645 here. And we're also going to plot its opposite, which is a negative 1.645. So if it helps, I'm just going to note that z is equal to negative 1.645 and z is equal to positive 1.645. You can kind of get a sense from what we did last unit of what's to come, right? The fact that we're going to be expected to find some values here. The region, the range of values. We're going to be expected to use the z-score to help us do exactly that. I want you to notice that with a 90% confidence level, our error is 10%, right? In which case we're going to split that between the tails. So each tail has 5% of that value. So we split between the tails. Good. Let's do this again. 95% confidence level. And again, we're just kind of seeing this, getting used to the visual so that we can prepare ourselves for what is to come. With the 95% confidence level, we see that our critical value is, excuse me, I'm so sorry, 1.96. Let's plot that point, 1.96, draw the dotted line up. But remember that we are looking at the middle 95%. So we also have the negative 1.96 to plot as well, which is right here. So that is negative 1.96. We're going to draw the dotted lines up, shade this middle region, which represents our 95% confidence level. In which case we see that alpha is 5%. So we're going to split that between the two tails. So 2.5% below and 2.5% above. Are we okay so far? Is this no big deal? Do we have any questions? Okay, we'll do one more.
I did something like this in high school.
For statistics?
Well, I didn't take statistics in high school. It was something for, I think, pre-calc, or algebra 2. It was one of those two classes.
I think it was
wow.
algebra 2.
Very cool. I love this. That's fantastic. So you have a little bit of insight into this exact concept. Very, very cool.
One of the big ones that I remember seeing is 95% confidence interval. That was the big one that I remember seeing.
Yes, absolutely. I would agree with you. That's definitely one of the most common ones you'll see. Actually, even in our notes too. I feel like
Yeah.
that's the most common one. Very cool. I love that. With our last one, 98% confidence level, our error is going to be 2%. So 98% confidence level refers to a critical value of 2.33. Same thing. Let's just label this 2.33. Then that means we also have its negative, its opposite. So negative 2.33. Draw the dotted lines up. We're just going to shade this middle region here, which represents 98% confidence level. If our error estimate is 2%, then each tail is going to be 1%. We split that between the two. Very, very awesome. I do want to make a comment here. We see that as the level of confidence increases, the width of the confidence interval also increases. Okay, so as the level of confidence increases, we went from 90% to 95% to 98%, and we can even draw those percentages in here. We see that that width increases, it gets wider each time. That is very interesting to know. Lucy, whenever you're looking at your critical values, your cutoff values, keep in mind they're always going to be the same value, but opposites, positive, negative. So in each case, they're positive and negative, and this is a 2.33. Since we were referring to the 98% confidence level, we go back to the chart here. Our 98% confidence level has a critical value of 2.33. So that's how you get your positive and negative values. Keep in mind, we're essentially identifying the middle 98%. So that's why we have a positive and a negative. Excellent. Very nice. Let's go ahead and turn the page. Stephanie, would you do us the honors of reading about the margin of error? And you don't have to read the formula. I'll do that. Just this first section on margin of error.
Okay. The margin of error denoted by E is the maximum likely difference with probability 1 minus A, such as 0.95, between the observed sample portion, P hat, and the true value of the proportion or the population portion, P. The margin of error, E, is also called the maximum error of estimate and can be found by multiplying the critical value and the standard deviation of the sample proportions.
Perfect. Thank you so much. First off, notice how they described the margin of error, capital E, okay, capital E. It's the maximum likely difference between the sample proportion P hat and the true proportion, population proportion P. Okay, so that's the margin of error. I want you to think of the difference between the sample and the population. The margin of error is also called the maximum error. And then check out the formula here. So Stephanie just read to us that you can find the maximum error or the margin of error by multiplying the critical value. Here's our critical value. And the standard deviation of sample proportions. This must represent the standard deviation of sample proportions. That's something interesting to note how they write the formula. I'm hoping this whole idea of P hat, Q hat looks familiar to you. And hopefully it's not causing you any anxiety thinking back to binomial distributions, right? The P and the Q, right? Success, failure, same concept here. Okay, P hat, population proportion, P, and then Q hat. So we're going to take a look at using this in just a bit. We still have to talk about the procedure for constructing a confidence interval for P. That's incredibly important. So we are going to use all of this information combined, but we definitely need to know how in the heck we even construct a confidence interval for P. Surujini, would you do us the honors of reading this section on the procedure, which by the way, please keep this in your minds as you move forward. So essentially, if you had a formula page, you're definitely going to want to write some of this stuff down. Surujini, all you.
Procedure for constructing a confidence interval for P. 1, verify the sample is a simple random sample. 2, the conditions of the binomial distribution are satisfied. There is a fixed number of trials. The outcomes of each trials are independent. There are only 2 outcomes, one of which we call a success. The probability of success remains the same for each trial. If we have 5 or more successes in a binomial experiment, n times P greater than or equal to 5, and 5 or more failure, n times Q greater than or equal to 5, then you can use a normal distribution to approximate a binomial distribution. Keep going.
Yeah, oh yeah.
3, evaluate the margin of the error E. 4, find the values of the interval limits. P hat minus, is
Don't
that
worry.
it?
Yeah, don't
Okay.
worry about that part. So essentially, these just show you ways to write the same thing. You have 3 options. Typically, we're going to see a lot of this first one. That's pretty standard when we write our descriptions, our interpretations. We usually use this first one as our to showcase the values of our interval limits. But you can write it in each of these 3 ways. And then the last?
Round the 3 significant digits.
Perfect. There are 5, thank you so much, Surujini. There are 5 specific steps here. Verify its simple random sample. The conditions of the binomial distribution have to be satisfied. Evaluate the margin of error E. So we're going to do this before we find the values of the interval limits using one of those 3 methods. Typically, we write it in the first one, where we have the lower bound less than the population proportion, less than the upper bound, right? Which includes your margin of error. And then, of course, make sure you round your answers to 3 significant digits as you do this, okay? Let's turn the page and see what the heck is going on. We're going to put all of this together, okay? So be prepared. If you're like, what in the hell? Come back to this page, read through this. This is going to be a very good guide in moving you through these problems. But actually, I'm hopeful that you won't even think too much of this. It follows a nice flow. And I feel confident that you will feel that way. Make sure you have your calculators handy. We are definitely going to be using these a lot today. So make sure they are near you. Excellent. A recent survey of 300 randomly selected, I'm going to stop there. This 300, what value does this take on? And all of the things we've done with statistics so far, this 300 would represent what variable?
N.
Yes, perfection. N is 300. Immediately when you're noticing these things, write it down. Identify what's happening here. Okay, start again. A recent survey of 300 randomly selected 4th graders showed that 210 participate in at least one organized sport during one calendar year. Okay, I'm going to stop right there. This is very interesting information. We're given a total number of 4th graders. And we are explained that 210 participate in at least one organized sport during one calendar year. What is our success? How do we figure out our success?
210 divided by 300.
Perfection. We're looking at a proportion. Very, very nice. So we're going to write here that P hat is equal to 210 over 300. We know this is the case because think of probability. Think about the likelihood of something happening. If you're told that 210 out of the 300 participate in at least one sport, we can actually convert that to a decimal so we have an idea of what percentage of those fourth graders actually play one organized sport at least.
I have that percentage if you want me to say
Yes, go for it.
70%.
Yes, perfect. In which case, what Nick is stating here is that our P hat value is going to be 0.70. Nick, if we know that P hat is 0.70, what's Q hat?
It would be 0.3.
Yes, perfection. So 70% versus 30%, 70% and 30% make 100%. Think back to binomial distribution. If you know one, you know the other, definitely. Thank you so much, Nick. We're next asked to construct a 95% confidence interval. Can you please turn back to your previous page with the table of common critical values? Go back to common critical values. And for 95%, what was that critical value?
1.96.
Yes, perfect. So we're going to write that Z is equal to 1.96. I'm just going to sneak that in here because, again, write all over it before you dive in. Might as well. Construct a 95% confidence interval for the proportion of fourth graders who participate in an organized sport during the year and write a confidence statement. Okay, we are ready to check this out. So we have to look at each of these pieces. Is it a random, I can't even talk. If you go back to the previous page, is it a simple random sample? Well, yes, we're told that they were randomly selected. So I'm going to make a note. Random. Is there a fixed number of trials? And if so, how many? Yes.
Yes,
Yes,
300.
300.
Yeah, 300. So we're going to say 300 fixed trials, because you essentially ask each student yes or no, right? The third piece is what are the outcomes? There can only be two outcomes. And yes, there are two outcomes, either yes or no on at least one sport. So there are two outcomes, either yes or no. Is the probability the same across the board? Is it essentially the probability of success remains the same for each trial? Yes,
Yes.
definitely. Probability of success remains the same. And then, of course, our last piece, we just want to verify that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. So essentially, we know that n is 300. So 300 times 0.70, we want to make sure that that's greater than or equal to 5. If you punch that into your calculator, I mean, it definitely will be. Think about 70% of 300, that's way larger than 5. 30% of 300, that's still way larger than 5. So those conditions are met as well. We next are going to look at the critical values. I'm just going to make a note here again. We're looking at 95% confidence, which means that our critical value, and I'm going to give you notation according to what we saw on our previous page, right? If we flip back just one tiny second, we saw that the notation for the critical value is Z sub alpha divided by 2, right? Because we split that that error between that error estimate between the two tails. So we're going to write Z sub alpha divided by 2. I want you to use this notation, okay? And we see that our critical value is 1.96. Now we're going to calculate our margin of error by using our formula. This is a formula you definitely want to have on your formula page. On your formula page, I would actually include all of the steps we saw from the previous page, the procedure, just so that if you're ever looking at these particular questions, you can go through each of the steps according to what your formula page says, okay? Even if we were meeting in person, you would be allowed to have a formula page. So I definitely recommend that you do this. Let's write out the formula for the margin of error. E is equal to, capital E is equal to the critical value multiplied by the standard deviation of the sample proportions. P hat times Q hat divided by N. So it's the square root of that value. So we're going to punch in all of these in. I would just say be really careful as you do this. We know that our critical value is 1.96. We're going to multiply that by the square root of, we see that P hat is 0.70 or 0.7. It doesn't matter, 0.70, 0.7, they're the same. Times 0.3 or 0.30, again, the same thing. Divided by N, which is in this case 300. There were 300 trials. My advice to you all is to take the square root of your fraction first. So this essentially becomes E is equal to 1.96 times, go ahead and punch this into your calculator. I want everyone to try this, so don't say anything out loud yet. I will share with you the solution once you've actually attempted this on your own. I want to make sure that we are punching this in exactly correctly. And go ahead and write down your value to 4 places after the decimal. Would you send it to me privately in the chat just so I can see your values? I got something a little bit different. Yep, okay, good. Okay, a couple areas of concern. Okay, let's double check this. Anthony, yes, you actually found the final solution, I believe. So let me just punch this in again for you, just so you can see. So we're going to take the square root. I'm going to use another set of parentheses because there's a lot going on here. So we have 0.70 times 0.30 divided by 300, and then we close the parentheses. And you should have 0.0264, and then we'll actually leave it as 0.0265. Abby, yes, the first part is proctored for sure. No, the first part is multiple choice and it will be proctored. The take home part, obviously they can't be proctored. And you'll have time to do that. As we get closer, we'll have conversations about that. We also have to talk about when the final exam is. I will explain to you what's going on. But we'll do that at the end of class. We're going to take 1.96, we're going to multiply that by 0.0265, and we find that our margin of error is 0.0519. Our margin of error is 0.0519. We are then going to write our confidence interval. Nick, go for it, no worries. We are going to write our confidence interval. Again, if you turn to the previous page, you can see each of these individual steps. But again, I'm going to write out the formula for you So it's going to be p hat minus your margin of error. That's going to bound the population proportion. And then p hat plus the margin of error. So we're trying to see where this, the true population proportion would sit. And we feel 95% confidence it will be within these two bounds. We use a margin of error to give us a little bit of leeway, right? I want you to think about it like that. We know that p hat is 0.7. We know that our margin of error is 0.0519. So all we're doing is plugging these values into our formula. It's nice because it takes away a lot of the guesswork. We're just simply plugging into our formula. Would someone give me my lower bound? Go ahead and share that with everyone once you punch that in.
0.6481.
Perfect. And your upper bound.
0.7519.
Perfect. We can write it as a compound inequality. We can also write this in interval notation. I'm just going to write it here just so you can see. Here we have it in interval notation. And now we're ready to write out our interpretation. Okay, check it out. We can say, we are 95% confident that P, our true value, of the population proportion of fourth graders that participate in at least one sport will be between 0.648, notice I'm rounding to 3 significant digits, 0.648 and 0.752. We are 95% confident that P, our true value of the population proportion of fourth graders that participate in at least one sport, will be between 0.648 and 0.752. This means we are 95% confident that 64.8 of students, all the way up to 75.2% of students will have participated in at least one sport. So out of all the fourth graders, we're expecting that 64.8% of them, up to 75.2% of them, will be the true population proportion of all fourth graders that participate in at least one sport.
Can we write like the percentage underneath, just so that when we go back to look at it, we can understand that it's a percentage?
Yes. I think we are confident that 64.8% up to 75.2% of fourth graders played in at least one sport. right? That's essentially what we're getting at. The true population proportion is somewhere in between those two values. We do not expect it to be lower than 64%, well, 64.8%. And we don't expect it to be higher than 75.2%. We're actually 95% confident it's within that range. That's what we're saying here. We are 95% confident that the percentage is within that range. Any questions on that concept? We've got another one, so we get to try this once more. Okay, all right, let's turn the page then. Practice number 3. You would like to estimate the proportion of students who are participating in clubs at MCC. You randomly select 1,500 students. I hope you're writing stuff down. As we're reading it, I hope you're writing the notation that you should be writing associated with what you're finding, and find that 900 of them are members of clubs. Just from that line alone, what pieces of information were we given? Give me one piece of information, anyone?
N is 1,500.
Yes, N is 1,500. That's the first thing. We know there's a total number of students in our sample. Excellent. Someone else, what's the second piece of information?
And that
P
hat. Oh,
Yeah,
sorry.
P hat, tell me more.
equals 900 over 1,500. Sorry, I cut whoever else that was off.
That's okay, I think it was the
That's
same.
okay.
I feel like it was exactly the same time. So yes, we want to know the proportion of success, the probability of success. So 900 out of the total, 1,500. When you punch this into your calculator, you should find a p hat value of 0.6. Someone else, what does that imply about q hat?
It's 0.4.
Yes, perfect. If we know 60% participate in clubs and 40% don't. So we want to construct a 99% confidence interval for the true population proportion of students who are participating in clubs at MCC and write a confidence statement. When you go back to your table, that 99% confidence interval. So again, someone else, so someone who hasn't spoken yet, what is the critical value for 99%?
2.575.
Perfection, 2.575. And we can sneak that anywhere, 2.575. I'm just going to sneak that there so we have all the information. Perfect. Let's talk about the requirements. Is this a random sample?
Yes.
Perfect. Are there independent trials?
Yes.
Yes, there are 1,500 of them. So 1,500 trials. Are there 2 outcomes?
Yes.
Yes.
Either you're participating in a club or you're not. So 2 outcomes. Yes. Does n times p, is n times p greater than or equal to 5 and n times q greater than or equal to 5?
Yes.
Yes. So both of those are in fact the case. We know that n is 1,500. 1,500 times 0.6 is definitely greater than 5. 1,500 times 0.4 is also definitely greater than 5. Excellent. For your critical values, we're just going to rewrite some of the information we put at the top. We know that we are referring to a 95% confidence interval. So 95% confidence level, which means that z sub alpha over 2, your critical value is 2.575. That's your z-score, 2.575. We're now ready for our margin of error. Again, it's just a formula, so we plug in. I'm going to write the formula for you once more. Capital E is equal to your critical value times the standard deviation of your sample proportion. So we've got 0.6 times 0.4. Oh, I was going to write it in general form. You guys go ahead. I'm just going to clean this up. Don't mind me. I'm going to write the general form before I plug in the values. That's what I intended. So I'm going to follow through on that. Okay, go ahead and fill in all of these values. Hopefully you are moving forward. I'm just going to fill in our values as well. Go ahead and punch everything in. Mike, excellent. Perfect. And I would like you to send me a message directly that gives me the margin of error. So what do you get when you punch in everything together? What is the value of your margin of error? So Mike has already shared that with me. Sam, perfect. Donna, there might be something tiny off with your answer, but pretty close. Angelica, you just missed 1 0, but you essentially have it. Anthony, thank you for the interval. Nicole, I have a different value for the, and I was looking for the entire thing. So punch in everything together. That might be it. Emma, double check that. Double check your entire expression. Punch that in once more. Leah, that looks great. Kelly, that looks fantastic. Surujni, that looks fantastic. Jenny, same thing, fantastic. Nick, yep, looks great. Beautiful. You should have 0.032 and then 57146. So we'll round to 6. There's our margin of error. And now we are ready for our confidence interval, which is written as p hat minus our margin of error. That's going to estimate the true population proportion, right? Plus and minus that margin of error. Good. At this point, we're simply going to take our values. What are you getting for the square root number? Let me show you. So by the way, just to punch everything in together, I would do 2.575 times square root. And then because it's opening up with this parentheses, I'm actually going to type everything in as 0.6 times 0.4 divided by 1500. Now you're probably thinking, why not use parentheses in here? The beautiful thing about your calculator is it follows the order of operations. So when you type in 0.6 times 0.4 then divided by 1500, your calculator will multiply before it divides because it has to follow the order from left to right. So that's how you can essentially plug in the entire value. Now, I could, if I wanted to, just plug in what's underneath the square root. So square root, I do the same thing, 0.6 times 0.4 divided by 1500. And then I'd close it and we get 0.012649111. That's what
So we don't have to use the parentheses again, because before you said to use 2 parentheses.
You don't have to, you can, but realistically, you actually don't have to. You can literally just punch it in as is because
Okay.
it will interpret the order of operations correctly. Yeah. And then of course, I would just start with 2.575, then I do times and then the square root of everything. So you should be getting 0.0326. Surujini.
I just wanted to add something for the calculation, because when I did the first one, I was getting something completely wrong. And if anybody's getting it, and when I was doing the second part, I added this fraction bar. Came
Oh,
out like I didn't have to worry about a mistake.
okay, so you did like this. So you said multiply by the square root and then how'd you write it?
I didn't put the parentheses in yet. I
Okay.
did my fraction bar after we did the take out that parentheses,
Oh,
the one.
that's automatic.
Oh, it did. Oh, mine didn't do that. So I just put my fraction bar and then I put the 0.06 on top times 0.04, and then it allowed me to put the 1500 at the bottom, and then I equal it, and it was because the first time I was getting it wrong when I tried the parentheses. So that's what I was saying.
I know exactly what you're talking about. So Pseudogenie's calculator, once she presses the fraction bar, it populates like a numerator denominator.
Yes.
And then
yes.
it lets her go to the numerator. Sorry, I didn't mean to do that. It lets her go to the numerator, type it in. It lets her go to the denominator and type it in. So that one's definitely a little bit fancier than this guy. So I think that's a great approach, especially if you want to just ensure that you're typing this in correctly. But yeah, if you don't have that, you have like, something similar to mine, you can just punch it in from left to right and top to bottom. So 0.6 times 0.4, then divided by 1500, then close the parentheses. But yes, I like that idea. You can definitely input your fraction so that you can select a numerator and denominator. Very cool. Very cool. All right, let's plug in our values. We know that p hat is 0.6. Our margin of error is 0.0326, less than the true population proportion. Then we have 0.6 plus 0.0326. So we're going to find each of these values. Leah has shared with us that she found 0.5674 for the lower bound. Emma found this as well. And then for the upper bound, she has 0.6326, and so does Emma. Donna, double check that you're punching in the values exactly as you see it. You should have 0.0326 for your margin of error, and then that will impact your upper bound as well. Okay, so double check that you're typing it in exactly as you see it, exactly as we have it here on this page. Okay. We can write our answer in interval notation if our heart desires. So 0.5674, comma, 0.6326. And now we can write our interpretation. Okay, that is. We are 99% confident that P, our true value of the population proportion of students at MCC who are members of clubs will be between 0.567, rounding to 3 significant digits, 0.567 and 0.633.
So for these, you want us to round to 3, that's it?
Yeah, for the interpretation, yes. Lumen may ask for these values to be rounded to 3 places as well. Same with your margin of error. So be prepared to potentially have to round each of these to 3 places. Good. I'm going to say this a different way just so that you are a little bit more comfortable with what we have written here in terms of our interpretation. We are 99% confident that if we went to MCC and we surveyed all of the students and we got the actual proportion of students who belong to clubs at MCC, it would be between 56.7% of the students and 63.3% of the students. That's what we are saying. If we went out and got every single student to respond, we are 99% confident it'll be within this range. The number of students in clubs, 56.7% and 63.3%. Awesome. If you turn the page, you'll notice.
I have a question.
Yes.
Can you go back to like C?
Yeah.
So, not C, I'm sorry. Yeah, C actually. So for the margin, I have like the first one, I have like a 0.0126, but when I times it like 2.575, it gives me 0.0347.
What I would do, Donna, I would keep the entire decimal as is.
Yeah, I was just gonna say she probably rounded it first.
Yeah. Don't round it. Let your calculator hold it. So
Okay.
just leave it in here and then do times 2.575.
Which I did, and still like, okay, let me try again.
Yeah, give that one more shot. You should have 0.0326. Or which is what we rounded to. So you should have 0.032571446. Okay, let me know if that was a success. Whoops. Good. While Donna's working on that, let's take a look at practice number 4. Take a look at this. This is very interesting. We actually are given a mini tab printout of the descriptive statistics. Check it out. So we are told that of 400 randomly selected nursing students, 35 said they plan to work in a rural community. What I'd like you to do is just take a moment to think about the information that you were given here, right? I want you to look at the descriptive statistics, look at the information that you were provided here, and see if you can discern what this is saying in terms of interpretation. So I just want to give you a few minutes. I'm actually going to pause the video while you think about this, okay? I'm going to pause the video now. Okay, so thinking back to how we have written our confidence statements so far, notice that we were actually provided with the interval. You see the interval notation here. So we were given this interval for our 95% confidence interval for that population proportion. So let's state the following. And both Emma and Kelly had pretty much identical statements. So we are, and I'm going to literally just jot down exactly what they wrote because it's perfect. We are 95% confident, and I'm hopeful that you had something very similar. We are 95% confident that P, our true value of the population proportion of nursing students who plan to work in a rural community will be between Now, here's the interesting piece. if we are going to round to 3 significant values, 3 significant digits after the decimal, 0.0598 would actually round up to 0.060. If we wanted to keep it to 4 places, then we can write 0.0598 all the way up to 0.1152. So I'm going to stick with the 3 places after the decimal, and I'm going to write it will be between 0.0 instead of 598. We're rounding to 3 places, so 060 and 0.115. Okay, so those are going to be your values.
I had that same answer. It's just in my head. I didn't write it down yet.
No, that's okay. That's perfect. Great. I love it. I just wanted us to have an idea of where we might be headed. So that's perfection, especially if you're including all of the values, you're including the label, you know, how we describe the true value of the population proportion, like what are we referencing? And then of course the lower and upper bound. So yeah, that's beautiful. That is perfect. Good. Because we have to have a serious discussion, I'm actually going to end it here. I know I'm ending a tiny bit early, but that's because I need to talk to you about the final exam. All right, so excellent work today. I'm going to stop our recording for our notes. Great job today.